Hi everyone, welcome to condensed lecture 17 and 18 for Physics 151. The main topic for this lecture is gravitation and applications of gravity, like weight, surface gravity of planets, and circular orbits, which will draw on what we just learned in the previous lecture about uniform circular motion. I'm going to skip a less important topic, which is Kepler's laws of planetary motion, although we'll briefly discuss Kepler's third law, which comes out of circular orbits. I'll be drawing on 3 or so examples from tutorials 17 and 18. And this lecture is relevant for the majority of online homework 16-18, which is a single assignment, but the majority of that assignment has to do with gravity and orbits. So let's start off with some theory, and we'll discuss Newton's law of universal gravitation, and then we'll get into some examples. So I'm sorry for the handwritten slides, but in the interest of time, this will just speed things up and instead of turning these into PowerPoint slides. So first of all, what is gravity? It is the phenomenon of the attractive force that arises between every mass in the entire universe. So anything that has mass, electrons, protons, atoms, planets, and stars, they all exert an attractive force on all of the other ones at the same time throughout the universe. By the way, there is no repulsive gravitational force. You may have heard of the term antimatter, but particles of antimatter, like positrons, for example, have positive mass just like electrons do. So they participate in attractive gravitation, just like all the other mass in the universe. We have a formula, which is Newton's law of universal gravitation, which helps us calculate the strength or magnitude of that gravitational attractive force. So the strength or magnitude of that force is equal to a constant of proportionality, which is the universal gravitational constant, big G. Capital G shows up in any table of fundamental constants in the back of our own textbook or any other standard physical textbook. It's considered one of the deep universal gravitational constants of nature, and it's thought that it probably has the same value everywhere in the universe. Then we have two masses. Mass 1 and mass 2 are the two objects that are doing the attracting to each other. And then there is the distance between those two objects. Now, if these objects are very, very tiny, like particles, or if we can pretend that they are point masses, then r is just the distance between those 2 points. However, real-life objects have some size. So this refers to the distance between the centers of those objects. We could think of this as the formal proper thing is the distance between their centers of gravity. But if we use the center of mass, for many applications, those are basically the same thing. This is an approximation if we take just the geometric center of objects, if the objects aren't perfectly spherical. But it turns out if they are spherical, then the exact answer you would get from doing all the calculus and all the complicated calculation is the exact same answer you get if you just pretended they were both points located at the centers of those spheres. So that's great. It turns out that stars and planets are usually spheres or something very close to spheres. So the answers we get from using this equation, if we pretend that that the stars and planets are just points located at the centers of those spheres, the answers we get are correct. All right. Now, if we think about this for a second, if we were to put in 1 kilogram and 1 kilogram for the two masses, and 1 meter for the separation between those two, right? So 1 kilogram is about the size of a moderate-sized bottle of water, right? A 1-liter bottle of water, for example. And if you had two 1-liter bottles of water and you place them 1 meter apart, what would be the gravitational force between those two bottles of water? The answer is it's extremely small. This is just a little more than a trillionth. This is actually it's about 60 trillionths. So it's 10 to the minus 11 order of magnitude newtons. So the gravitational attraction between those two bottles of water is going to be on the order of like 10 billionths of a newton. Remember that 1 newton is a fifth of a pound. So this is a puny, puny force. As a result, this value of big G, the gravitational constant, was very hard to measure. So Newton wrote this equation, came up with this equation in the mid to late 1600s, but it wasn't until a century later that Henry Cavendish was finally able to devise a lab experiment to measure this with any accuracy at all. And even to this day, if you look in a table of physical constants, big G is going to be one of the ones that is known to the fewest decimal places compared to, let's say, the elementary charge or the mass of a proton, which are known to many more decimal places. All right, so great. So this is a formula that tells us the strength of that attractive force. And we're going to reflect on this formula just a little bit more. This is just a modern version of the apparatus that Cavendish used to make that sort of a measurement. But I'll skip this for now. So let's reflect on this a little bit more. This is just what I was just saying in the previous slide. Because G is extremely small, that means that the gravitational force between everyday objects that we encounter in daily life, like people, for example, which are maybe 50 to 100 kilograms, if you put two people 1 meter apart, the gravitational force between them is still going to be 10 to the minus 7, 10 to the minus 8 of a Newton. So that's actually one of the example problems in tutorial 17, and I'll leave it to you to try calculating that just as an example. But that sort of incredibly weak force, less than a millionth of a Newton, means that it doesn't affect our lives. When a group of people walks by us, we don't suddenly feel some force pulling us out of our seats toward them. Let's think about the proportionality of this equation. Notice how the strength of the force is directly proportional to each of the two masses. So if we have two masses, and if I were to double one of the masses, then that would exactly double the strength of the force that each of the masses exerts on each other. So doubling one of the masses would double both of the attractive forces. It's easier to see the force vectors on this one right here, right? So here's the attractive force of A toward B and the attractive force of B toward A. And if I were to double the mass of A, both of these two force vectors would get twice as large. If I were to double the mass of B, each of the force vectors would also get twice as large. So that's a direct proportionality in the numerator. Notice, however, in the denominator, the separation between the two masses here, it is an inverse square proportionality. So what that means is if we were to double the separation between the two masses, then we would find that the strength of this force, that by putting in twice as large of a value for R here in the denominator, when you square that twice as large, you get a 4 times larger denominator. And that means that the force between the two masses will become 1/4 as strong as it used to be. So just to summarize that, if the force between two masses is F naught when the two masses are distance d apart, then if I double the distance, the strength of the gravitational force on either one will become 1/4 of F naught. If I tripled the original separation, the strength of the two forces would be 1/9, quadrupling 1/16, 5 times original distance 1/25, and so on. So you can see the pattern here. This is an inverse square proportionality. This shows up in nature in a lot of other ways as well. If we have a point source of light or a point source of sound, then the intensity of that light or sound will drop off as 1 over the distance squared. So if you get 3 times farther away, that light will appear to be 1/9 as bright. You can ask the question, how far must you separate two objects before they will exert 0 gravitational force on each other? And you can see by this equation, if you ask the question, what should be the value of R so that F is 0? Well, R would have to go to infinity. So in other words, any two masses in the universe always exert some tiny non-zero gravitational force on each other. However, because this is an inverse square proportionality, the strength of this force drops off very quickly. So as a result, you can neglect the gravitational pull of masses that are far from you, like cosmically far, unless their mass happens to be incredibly huge. But their mass would have to be incredibly huge squared in order to make up for the fact that the object is far. So we don't worry about the gravitational, even though the mass of Jupiter is very large, and even though the mass of the Andromeda Galaxy is ginormously large, we don't worry about their gravitational forces acting on us in daily life because they are so distant. Okay, so this is just a good thing to memorize, and we'll do some more examples with this coming up later. The last thing to talk about, we've mentioned the strength of the gravitational force. So the last thing to talk about is the direction of the gravitational force. And as you probably gathered from my little sketches here, it's attractive. So each of these two masses is attracted to the other. Okay? And therefore, the gravitational force always acts along the imaginary line that connects the centers of the two objects, right? Technically, those centers of gravity are centers, centers of mass. But for our intent, I'm just going to use the term centers. So if you think about that imaginary line, then the attractive gravitational force will act along that imaginary line. As we look at these two attractive force vectors here, what do we see? We see that their direction is opposite. Okay, one of them is to the upper right, the other one is to the lower left. And we also see that their strengths are equal, because notice we would get the same force strength if we were to swap the two positions of mass 1 and mass 2. So if we calculate, for here it's mass A and mass B in my sketch, if we calculate the force of B acting on A, we're going to get the same number of newtons as if we calculate the force of A acting on B. So what we find is that we have two forces that are equal in strength and exactly opposite in direction. Could this be a Newton's third law pair? Yes, in fact, indeed, this is. Remember what Newton's third law says. If object A exerts a force on object B, B must exert an equal magnitude and opposite direction force on A at the same time. So any of these attractive forces between masses for gravity, or attractive or repulsive forces between electric charges, which you'll learn in physics 152, or magnetic poles, and so on, those are all Newton's third law pairs. Okay, I'd like to do some examples with Newton's law of universal gravitation at this point. So um, let me switch to the video and we'll do a couple examples from tutorial number 17. Okay. All right, great. So I'm going to solve problem number 1 and then part of problem number 4 as examples of applications of Newton's law of universal gravitation. So suppose you have a situation where while standing on the Earth, you see the sun setting in the west in front of you, and then you turn and you find that the moon is rising in the east right behind you at the same time. And you're curious to know what's the strength of the gravitational force that each of those celestial objects is exerting on you at that moment. So that's what this question is asking. What is the strength of each of those forces? And then if we add the vectors together, what will be the sum of those two vectors? And how do those compare to your weight from the Earth's attraction? Okay. All right, well, let's sort of just sketch the situation. So we can imagine that we have the sun right here, and then we have you standing on the Earth. So I'm not going to draw the Earth for the moment, just to keep the picture simple. So it's you. And then we have on the other side of you, out in space somewhere, we have the moon. So this is completely not to scale, right? The distance between you and the moon is much smaller, than the distance between you and the sun by the factor of like 100 or so, okay? And of course, the masses are all very different, and the sizes are all very different. So we're given all of these masses right up here at the top, or we could just look them up in any table of astronomical constants, like we have in our textbook, or that you can easily find online. So the sun exerts an attractive force on you, and at this moment, we don't know which of these two forces is going to be stronger. So I'm just going to call this the force of the sun, right? S for sun. And then the moon is going to exert an attractive force on you, and I'll call that the force of the moon. Right? And they're in opposite directions. And in order to calculate each of those forces, we're going to use Newton's law of universal gravitation to get the strengths of each of those forces. The force of the sun on you is going to be equal to G, the mass of the sun, times the mass of you, divided by the distance between the sun and you. All right, well, what is that distance? Well, up here, we see that the separation between the Earth and the sun has an average value of 1.5 times 10 to the 11th meters. You're on the Earth, so therefore we can safely use that value of the Earth-Sun separation. So we'll safely use that value of the Earth-Sun separation to be the distance between the sun and you. Okay? Now we'll plug in the values. So I look up the value of the gravitational constant, but I've also put it there at the start of the tutorial just to save you time. Mass of the sun, and then the mass of you. And I just said, let's set the person's mass to 100 kilograms. And the separation between the Earth and the sun is 1.5 times 10 to the 11th meters. Now, if any of these were not in MKS units, we would need to convert them. Because notice how capital G is in MKS units, and that will also give us the force in newtons. But if we were given any masses in grams or any distances in kilometers, for example, then we'd have to convert to get newtons at the end. Also, this square in the denominator is very easy to forget, so make sure that you include it. I ask my calculator what the answer to that is, and I get 0.590 newtons. All right, so now we know the force of the sun on you is about 0.6 of a newton. Remember, a newton itself is about 1/5 of a pound. So that means that the force of the sun on you while you're standing on the Earth, or while you are existing on the Earth, is really kind of like a quarter of, it's about 1/10 of a pound. It's extremely, extremely weak. Right? So it's not something that you would notice as the sun changes its position with respect to you, for example. If we calculate the force of the moon on you, let's set it up. We have big G times the mass of the moon times the mass of you divided by the separation between you and the moon. Well, for that, let's use the Earth-Moon mean separation. So let's use the Earth-Moon distance. And as we plug in those values, now we're going to use the mass of the moon. So this is, big G has the same value as before, the mass of the moon, mass of you, and then the Earth-Moon separation. And my calculator tells me that that comes out to be about 0.0033. So that's about 100 times weaker still than the gravitational force of the sun on you. So knowing that, actually, I can kind of correct my diagram a little bit and make it more accurate. And the force of the moon on you is 100 times weaker than the force of the sun. So this little vector should actually be 1/100th as long as the big vector. Less, even less so, or 1/200th. If we were to ask them what's the vector sum of those two forces acting on you, F total is going to be the force of the sun vector plus the force of the moon vector. So what does that look like? It's, if I do a little graphical sketch, the force of the sun is to the west, and we're going to add tip to tail the force of the moon, which is to the east. So the sum of those two is going to be from the start of the first vector to the end of the last vector. So this is F total. And if I just then do the sum of these two, F total, F sun is 0.59 newtons to the west, F moon is 0.0033 newtons to the east. That means that F total is going to be equal to 0.587 newtons to the west, right? In other words, toward the sun. So it's just a one-dimensional vector addition, pretty straightforward. What is our weight from what is the strength of our weight from the Earth? So while we're standing on the surface of the Earth, we know that our weight is equal to m times little g for the Earth, okay? So that's going to be 100 kilograms times 9.8 meters per second squared, and that's 980 newtons. So again, the force of the sun acting on you is something like 1/2000th as strong as the force of the Earth acting on you. And then the force of the moon acting on you is 1/200th of the force of the sun. So it's down in the order of like a millionth of the force of the Earth acting on you. So these two forces are pretty negligible as far as we're concerned in our daily life. Now, it's not to say that the sun and the moon don't exert strong gravitational forces, generally speaking. Their gravitational forces on the Earth are significant. And of course, we see how they can raise tides on the Earth, for example, right? The moon raises substantial tides, and the sun raises tides that are about half the height of that the moon raises. All right, great. So that's problem number 1. Let's jump to problem number 4 now. And I'm going to leave the conceptual parts A and B for you as an example. We already talked about the proportional reasoning that goes into Newton's law of universal gravitation. So I'll let you think about parts A and B. And I'll focus on part C. So suppose that we have 2 planets here, and whether they're in motion or not doesn't matter, right? Newton's law of universal gravitation doesn't care whether mass m1 and m2 are moving or not. It's just whatever their separation is at that instant. That's what we plug into the Newton's law of universal gravitation for the value of r. Suppose that planet D over here on the left has 5 times the mass of planet E over on the right. So we don't know what the mass is in absolute kilograms, but we just know that D is 5 times greater than E, or 5 times the mass of E. Okay? So put another way, right? The mass of planet D is equal to 5 times the mass of planet B. If you wanted to write that algebraically. And suppose that their centers are a distance L apart. So the separation between these 2 centers is L, capital L. Now, suppose that, where could you, along the imaginary line that connects the centers of these 2 planets, where could we put a tiny little spacecraft, so we're going to assume a relatively small mass, so that it experiences 0 net gravitational force from the 2 planets? Okay, so, well, we know that if we put it right in the middle, we know that Newton's law of universal gravitation. Let me write that down. So this will be mass of the planet times mass of the spacecraft, all divided by the separation between the planet and the spacecraft, right? Squared. All right. If we were to choose a point exactly halfway between the 2 planets, then the separation between either planet and the spacecraft would be exactly the same. G is exactly the same. The mass of the spacecraft is the same. So all that, the only thing that would affect the strengths of the 2 forces is the masses of the 2 planets. So if planet D has 5 times the mass that planet E does, then we would expect that planet D would exert a force that's 5 times as great as planet E does. So if this is our little spacecraft, then I'm just going to draw as a dot. Then it would, planet D would exert a force that's 5 times as large as planet E would. Okay. So the question that part C and D are asking is, it would stand to reason that if I move the little spacecraft, if I were to move the little spacecraft closer and closer to planet E, first of all, we know that the strength from planet E would then, the strength of the force from planet E would then grow as we get closer and closer to it. And the strength of the force from planet D would weaken as we get farther and farther away from planet D. So as the force from E grows and the force from D weakens, it would stand to reason that there's some point over here off to the right where those two forces should exactly balance each other out. So in other words, if I were to try and just sketch that right below, okay, I will sketch it right here. There should be some location over here so that the strength of the force from planet E has grown and the strength of the force from planet D has weakened. And they're now exactly the same strength in opposite directions. And if we were to sum them, they would sum to 0. So let's try and figure out where that is, where that can occur. So we're going to solve for this distance. I'm going to call that distance, that unknown distance, D. You can call it anything you like. We know that the distance between the two planets is called capital L. So therefore, this separation over here between the spacecraft and the right-hand planet must be L minus D. Okay? All right, so good. So keep that in mind. Unfortunately, I have to move it up off the screen, but keep that in the back of your mind. So now, what we're going to do is we're going to say, all right, at our desired position, the sum of the two forces acting on the little spacecraft, the sum of the vectors should sum to 0, which means that the magnitudes must be equal. Right? So the only way for the sum of these two force vectors to sum to 0, because they exactly point opposite each other, would be if their magnitudes exactly match. So we can say, all right, then that must mean that their magnitudes must be exactly equal to each other. Now we know what the formula is to calculate the magnitude of a gravitational force. It's Newton's law of universal gravitation. So the strength of the force of planet D is going to be equal to G, the mass of planet D, times the mass of the spacecraft, divided by the separation between the two squared. So the separation between D and the spacecraft squared. Then we're going to have a similar looking expression over here on the right for planet E and the spacecraft. Now let's plug in what we know for all of these quantities. We know that the mass of planet D is 5 times the mass of planet E. And we're going to plug in these expressions for those two separation distances. So this becomes G 5 times the mass of planet E, mass of the spacecraft, G mass of E, mass of the spacecraft. And then in the denominators, this is D squared and L minus D squared. Well, now it looks like a lot of this is going to cancel. The mass of spacecraft cancels out. The gravitational constant cancels out. The mass of planet E cancels out, leaving a 1 in the numerator here. And we're left with a 5 in the other numerator. So we can just cross multiply. And this becomes 5 times L minus D squared is equal to 1 times D squared. That's great. Now we can pretend L is a quote unquote sort of a known quantity. So that will allow us to solve for D, the distance to the right of, a little d, pardon me, which is the distance to the right of planet D, and allow us to solve for that in terms of L. So all we have to do is just solve for little d here, and we will have answered part C. All right, so let's do that. It looks like I can take the square root of both sides. Now it turns out if you do that, there's actually two equations that you would get. You would get, when you take the square root, remember there's two answers, plus and minus. So let's write out the plus equation first. And then over here on the right, I'm going to write out the minus equation. If I solve the left-hand equation for little d, I get the value square root of 5 divided by square root of 5 plus 1 times L. There's more than one way to write this. They all look kind of the same as far as how algebraically simplified they are. So another way to write this is 1 over 1 plus 1 over root 5. But I'll just leave it this way. On the right-hand side over here, I get square root of 5 over square root of 5 minus 1 times L. Well, it turns out this expression here is greater than 1. This lies, so what that means is little d is greater than 1 times L. That means that that's talking about a position that lies over here somewhere, right? It's greater, the distance to the right of planet D is greater than L. All right, well, what does that represent? It turns out, actually, mathematically, we've just solved for all locations in space for which the magnitudes of those two force vectors are the same. So it turns out if you put the little spacecraft over here, it's true that the attractive force from planet D and the attractive force from planet E will both have the same magnitude. They'll both be the same number of newtons. But the problem is here, they're not canceling each other out, right? If this is our little spacecraft right here, then both of these attractive forces are both tugging the spacecraft to the left, and they're not summing up to 0 at all. But the two magnitudes are equal, so mathematically, the math told us that that is an answer to the question that I asked, right? I asked the mathematical question, where are these two magnitudes, where in space would these two magnitudes be equal? Well, it turns out that's one of the locations. But we're going to discard that answer because this is outside, right, of the region between the two planets of length L. This is the answer we want. And if I ask my calculator what that is, that's approximately equal to 0.691 times L. So just for my sketch here, that would be about 0.7 L. So it's kind of close to where we drew this little spacecraft right here. 0.5 L would be dead center. 0.7 L would be around here. Okay, great. It turns out you can show part D, I just asked, what if you don't know that one of the planets is 5 times the mass of the other? You just know that one of the planets is k times the mass of the other, where k is any value bigger than 1, right? So you just have an asymmetric balance. We have one planet that's more massive than the other, but k is the ratio of the masses. Then what would be the solution for the location? You could show that in that particular case, D is simply equal to, if you just replace 5 here by k and do the exact same calculation, it's equal to root k over root k plus 1 quantity times L. So the more imbalanced the two masses are, or the closer to equal the two masses are, the closer this gets to 0.5. So in other words, the balance point would get closer and closer to dead center. In fact, if k is exactly equal to 1, then this becomes 1 over 1 plus 1, which is just 1/2. If k becomes very large, right, then what happens is that that coefficient becomes a bigger and bigger and bigger decimal. Until finally you can see that if little k is really ginormous, right, so that planet D is massive compared to planet E, you would have to almost be sitting right on top of planet E for the two forces to balance out. So as k becomes extremely large, if we explore the extremes here, if k is extremely large, then the +1 becomes negligible, and this approaches root k over root k, which approaches unity. So D, the position where you should place the spacecraft, is basically almost at planet E. That's what we would expect, right, in that particular case. All right, good. So just doing a sanity check on our answer, exploring the limits of the two extremes helps give us confidence that this is the correct algebraic expression. You can also double check. You can, now that we know where to position the spacecraft, you can put the spacecraft at this location and then go back and actually calculate what the value of this expression is for both planet D and planet E acting on the spacecraft when the spacecraft is there. What you'll find is that these two are both equal to about 10.5 or so of G mass of E times mass of spacecraft over L squared. So it turns out they're exactly the same. So that's good. I think that means we got the right answer. All right, let's go back to the lecture slides. So that was Newton's law of universal gravitation. That is the sort of basic theory that helps us calculate what the strength and direction of the attractive gravitational force is between any two masses. So now let's look at one application of that, and that is to figure out what the weight of an object is on any generic planet. So what we can do is we can say, all right, suppose we define weight as the weight of a small object, little m, as being the mass of that little m times some quantity that we're going to call the gravitational acceleration, right? Or the local value of little g is what it's sometimes called, right? The local value of little g. So we're going to define, and remember how weight was defined. Weight was defined as the gravitational force of a planet acting on that little g. I'm sorry, that little m, that mass little m. Well, we now have an expression, Newton's law of universal gravitation, for the gravitational force of a planet acting on the mass little m. And it's equal to this. So if we set these two expressions equal to each other, what do we find? We find that the mass little m cancels out. And we wind up with an expression for the local value of acceleration due to gravity as equal to big G, mass of the big planet, divided by the separation between the center of the planet and the center of the mass little m. So if you're at some height above the surface of the Earth, then this expression tells you the value of little g at that location. So if we have a spacecraft or a space station or any satellite or moon that's out here, we could find out what the value of little g is at that location above the surface of the Earth using this expression. If you want to talk about right on the surface of the Earth, well, then you just plug in the value of the planet's radius for that separation between the mass m, the hypothetical location of mass m, and the center of the planet. And there you go. That becomes the expression for the surface gravity then. Okay. So the only tricky thing about this is if you're given a problem where you have some height above the surface of the Earth, you need to make sure that you don't just plug in the height, but that you plug in the height plus the radius of the planet to get the total separation between the center of the planet and the center of the little object that you're trying to weigh. And that's because that's what little r is in Newton's law of universal gravitation. It's the distance between the centers of the two masses, not the surfaces of the two masses. So let's do an example with this. You can see down here at the bottom, this is actually question 5 on the tutorial. It says, using the physical values for the Earth's radius and mass, calculate the value of surface gravity for the Earth and see if it's close to our value 9.80 that we've been using all along. So if I just look up the astronomical values for the mass of the Earth and the radius of the Earth, I can plug those into our equation for surface gravity, and I calculate it, and sure enough, it comes out to be very close to 9.80. So remember, this is actually the value of little g near the Earth's equator, and then it increases to about 9.82 up at the poles, and it does vary a little bit over the surface of the Earth due to like the thickness, varying thickness of the Earth's crust, and the fact that the Earth bulges a little at the equator, and other non-uniformities in the distribution of the mass inside the Earth. Okay. All right. I think that um, I think that's good enough for the example here for surface gravity. And let's just move on to the last bit of theory, which is that of circular orbits. So I'm going to introduce this by first sort of asking this sort of question of what is an orbit. And to ask that, oh, I'm sorry, I'm gonna skip this. This is just showing that the strength of this local value, this value of local little g, drops off very quickly with distance. It drops off as 1 over r squared from the center of the Earth. So, and 1 over r squared once again drops off relatively fast. However, I will add this. Notice that it is far from 0. So you can be at 1 whole Earth radius above the surface of the Earth, and notice that the value of little g is still something like a quarter of what it is on the surface of the Earth. So there's plenty, it's a total misnomer when we say that an astronaut is in low Earth orbit in the space station, which is basically just like right here, like 1/10 of an Earth radius above the surface of the Earth. The value of local value of little g there is still like 90% what it is on the surface of the Earth. So the space station and the astronauts that are in orbit, they have plenty of weight. There's a very strong gravitational force acting on them from the Earth, and so they have lots of weight. They are not weightless at all. Instead, they are in free fall, and that's what I'm about to introduce on the next slide. So let's think about a hypothetical situation here. Suppose we could climb a really tall tower, which is not shown here, right, off the surface of the Earth, and then we could fire a cannonball or some sort of other projectile off the top of that tower. If we were to fire it at a very low speed, then what would we see? We would see that it would basically go a relatively short distance. It would be attracted toward the ground, and it would not travel very far before it hits the ground like that. What if we could double the launch speed? Again, firing it horizontally, tangent to the surface of the Earth. Then what would we find? It would land farther away, and instead of landing at the same height, by the time it gets over to that greater distance, the Earth has also curved away. So the projectile would fall further in the vertical direction. The height through which the projectile would fall would be greater because the Earth is curving away from it when we fire it with so much speed that it's able to actually travel a significantly larger horizontal distance. What if we were to double the speed again? Same thing. By the time it actually gets down to the height of where the ground was, it's way over here, and the ground has fallen away significantly. So it keeps falling toward the ground, and the ground falls away even more. You can see that eventually we'll get to a speed where every time our projectile travels a certain distance horizontally, it falls a small distance vertically, and that distance that it falls vertically is exactly the same amount by which the ground has fallen away from horizontal as well. It's a pretty fast speed for that to happen. In fact, based on the size of the curvature of the Earth, an object would have to go about 5 miles or 8 kilometers every second so that the amount it falls vertically matches the amount by which the Earth is curved down. So that's about 8 kilometers per second or 5 miles per second would be the speed you would need. But if you reach that speed, which is about 18,000 miles an hour, then what you would find is as you move sideways, you're falling toward the surface of the Earth forever. You're always falling toward the Earth. You're always falling toward the Earth as you move sideways. And the Earth is falling away from you, is curving, I should say, not falling, but curving away from you at that same geometric rate. So you're forever falling toward the Earth, and never hitting the ground because the ground keeps curving away from you as well. And then eventually you'll come back to the same location and keep falling toward the Earth and falling toward the Earth forever. So notice, orbit is simply free fall while that object possesses a very large tangential velocity. That's all it is. You can imagine there is one very special tangential velocity that allows you to have exactly a circular orbit. If you're a little shy of that tangential velocity, oh, and that, by the way, that tangential velocity is, like I said, for the Earth, when you're near the surface of the Earth, it's about 18,000 miles an hour. And if we go away from the, if you're higher up at a greater and greater radius from the Earth, then that speed is actually slower. So you can calculate it based on what distance you are from the surface of the Earth, and we'll learn that formula on the next slide. If you're shy of whatever speed you need for that perfect sort of circular orbit, right? Meaning that for every amount you go sideways, you fall gravitationally a certain amount vertically, but the ground curves away by that same amount vertically. If you're not going fast enough horizontally, then it turns out that this shape right here is not a circle. This shape of this orbit right here is elliptical. And actually, you can draw an ellipse, which I didn't. Let's see, I can draw it with my stylus here. We could draw an ellipse that would start here and go this way. It would graze the surface of the Earth on this side and then go back out to there. Okay, so that would be an elliptical orbit. If we launch that cannonball with a speed that's less than 18,000 miles an hour, then it would, but still the tower is tall enough that the cannonball doesn't quite hit the ground, right? It gets close to the ground, but then it'll come back out. Or if the Earth itself were smaller, if the Earth had the same mass, but it was more compact, suppose that we just, were able to crunch it into a much smaller spot. Then if we launched our cannonball from the same location, then we find that it would execute this sort of an ellipse, like this, where it has a near side and it has a far side of the ellipse compared to the center of the Earth. Right? So a circle is also, if you've learned some analytic geometry, then you know that the ellipses are a whole family of curves. They get more and more eccentric or elongated, and or less so. And if you make them the least eccentric or least elongated, then it's a perfect circle. So a circle is just a special case of an ellipse. What if we go the other direction and we launched this cannonball with a speed that's greater and greater than 18,000 miles an hour? What if we launched it with 20,000 miles an hour, for example? Then what we would find is it would trace out a bigger ellipse that heads out that way, and it goes off the screen and it comes back around from the other side, like that. So in that case, the spot shown here is the near point of the ellipse, and the far point is way below the bottom of the screen somewhere. So those are also ellipses. What if we made the speed even faster? So instead of 20,000 miles an hour, we did 22,000 or 24,000. Then what happens is this ellipse would get bigger and bigger until finally there comes a point, a speed at which the far side of the ellipse is actually at infinity. Okay, so the ellipse gets bigger and bigger and bigger until finally you could launch at about 25,000 miles an hour for the Earth. And what would happen then is the far side of the ellipse happens at infinity, which means the object never gets there, which means it never does come back around from the other side. So suddenly that's not a closed orbit anymore. It's technically a sort of a one-pass orbit, if you will, of the Earth. And those are called unbound or open orbits, as opposed to the ellipses we've been drawing, which are closed or bound orbits. Okay. If we fired the cannonball with even more than 25,000 miles an hour, what if we did it with 30,000 or 40,000, 50,000 miles an hour, well, then the same sort of thing's going to happen. It's just going to head off into space with a little bit of a curve because the Earth is still tugging on it. But the shape of those curves now are hyperbolas. So they're even more open than the green parabola, which is what happens at 25,000 miles an hour. So the green parabola at 25,000 miles, that 25,000 mile an hour boundary between closed orbits and open orbits, or bound orbits and unbound orbits, that's called the escape velocity for that particular planet, so or object. So that is 25,000 miles an hour roughly is the escape velocity, and that gives you that borderline case between ellipses, which repeat, and hyperbolas, which are open. And a parabola, as you know, is also open, but it's the limiting case between the two. All right, so hyperbolic orbits do happen. For example, when we fire a spacecraft on a slingshot past Jupiter or past Venus, then that is a single pass, and it's a hyperbolic orbit coming in in this case it'd be something coming in from the left and then going out to the right, and that's it. And it doesn't repeat past that planet. Right? It doesn't come back around again. There was a famous in 2017. There was a famous interstellar asteroid that came in from who knows where, from elsewhere in our galaxy, and it made a single pass past our sun. And that the name of that interstellar asteroid was Oumuamua, and it was an interstellar visitor. It had so much speed that it was far greater speed than the escape velocity for the sun. So it was one pass. The sun bent its path a little bit, and it left, and it'll never return, according to our calculations. Right? It has way too much speed to ever slow down and come back to our sun again. Unlike all of the other comets and all of the other planets that orbit the sun over and over. Those are all in bound or closed orbits. All right, well, so that's the general background of orbits and what orbits are. So the main thing I want you to realize is orbits are not, all they are an object with so much tangential speed or tangential velocity that the planet underneath curves away at the same speed or faster than the object itself falls toward the planet. So as a result, objects that are in orbit are forever falling toward the ground, but the ground just keeps curving away at a rate equal to or faster than the object's rate of fall. So the object never hits. So if you wanted to put something in orbit, so what this means is, if you want to put something in orbit, you have to give it a very large tangential velocity. And that's what we do when we launch a rocket from the ground. We launch it up into the air, and we keep giving it more speed and more speed and more speed and more speed until finally the rocket is out of fuel. But at that point, it takes several minutes to do this, but at that point, you've built up its speed into the thousands and thousands of miles an hour. And then it'll be in whatever sort of orbit you want it to have. A bound orbit to orbit the Earth, or if you want to get away from the Earth and go to interplanetary space, you need to exceed the escape velocity. All right, so let's consider now the very special case of exactly the circular orbit, because we already know the physics for uniform circular motion. So we already learned that for uniform circular motion, there has to be some net force, and let's consider a little mass, which I'm going to call little m, okay? Then in order for that mass little m to orbit a large mass, big capital M, then there needs to be a net force acting toward the center of the circular motion. Well, we know that that net force is provided by gravity. For circular motion to result, we know that the strength of that net radial force has to be equal to m times v squared over r, and it always needs to be directed toward the center of the circle. We know that gravitational force is always attractive between the two masses, so that satisfies the direction, right? Even as one of the masses moves, the gravitational force will always still be toward the center of that circle. And we know that it's given by Newton's law of universal gravitation. So if we write the law of universal gravitation between mass capital M and mass little m, and if we set that equal to the centripetal force needed to keep little m in a circular path, then we notice that 1 power of r cancels and the mass of little m cancels. And we get an expression for the speed that you would need to launch that cannonball at in the previous slide, so that it would exactly execute circular motion from that point onward. Okay, so what speed would you need to get your object up to, tangential speed, so it'll have circular motion? This is the answer. If you exceed this speed, you wind up with an ellipse, or if you really exceed it, you wind up with one of those unbound orbits. And if you're short of this speed, you wind up with an ellipse that goes the other way, and if it doesn't graze the ground, you might just smack into the ground. But if you exactly match this speed right here, then the result will be a circular orbit or uniform circular motion. We can do one more bit of physics and say we also know from our previous lecture that for uniform circular motion, the speed that an object travels at must be 1 circumference per period. So if we use that expression on the left-hand side here, we now have an expression that relates the period of one orbit to the size, the physical orbital radius of that orbit, right? So the size of the circle that's being executed. Notice that it depends on the mass of the central body that's doing the pulling, but it does not depend on the mass of the little body. So as long as the small body is indeed far, far less massive than the big object, then notice any little object that you happen to put into a circular orbit, any little object that you give the same speed at the same distance will execute a circular orbit. So if we were to ask the question, what speed must a golf ball have in order to orbit the Earth at a distance of 10,000 kilometers? The answer would be the same for the golf ball as it would be for a Tesla car, as it would be for a rocket booster. All of them are the same because that speed does not depend on little m, the mass of the orbiting object, just big M, the mass of the central body that's doing the pulling. And if we were to ask the question, what would be the period of a planet orbiting the sun, if the sun is the central body, at a distance r, notice you don't need to know the mass of the planet. It doesn't matter if it's a little planet like Mercury or a giant planet like Jupiter, right? Just as long as the mass of the planet is far less than the mass of the sun that you're talking about as the central body. It turns out this is recognized as one of Kepler's laws of planetary motion. Kepler didn't know this constant here. He just found that the ratio between the proportionality between the period and the orbital radius of planets orbiting the sun was equal to a ratio of period squared over orbital radius cubed. So Kepler was a very talented mathematician. He was able to figure this out, even with the very limited observational tools and everything of the time in the early 1600s and late 1500s. But he didn't know why. It wasn't until after Newton, and after we knew Newton's laws of motion and conservation of energy, that you can actually show what this constant is right here, and you can show that the shapes of orbits need to be the so-called conic sections that we were talking about before. Circles, ellipses, parabolas, and hyperbolas. So this is also nicknamed Kepler's third law, but as you can see, it just comes from the uniform circular motion material that we learned last lecture, combined with Newton's law of universal gravitation from this lecture. So this is just a really handy equation because it directly relates orbital radius with period. The one last little warning I'm going to give you before we do an example with this is notice that big G, if you look it up, is in MKS units. So that means you have to make sure that orbital radius, mass of the central body, and period are all in MKS units as well. That's a little inconvenient because usually, although masses are often in kilograms, that's not so bad. Periods are often given in days or years, and you need to convert all those into seconds. And then distances, it might be in kilometers or light years or anything else, you need to convert into meters. And that way this equation will balance out and it'll work. Okay, and the same is true for this equation. Big G, again, is in MKS units. Okay, so that's it for the theory slides. So let's do one last example of an orbit example, and then we'll be done with lecture 17 and 18. So I'm going to switch back to the video camera. Okay, and here we have tutorial 18, and let's just do example 1, right? Examples 2, 3, and 4 are very similar, and they'll use the same equations. So suppose that we have a small satellite in circular orbit just above the surface of the Earth, just grazing the surface of the Earth. Okay, so if we imagine that this is the surface of the Earth, or yeah, that this is the Earth, then let's imagine that an object has some tangential velocity so that it can orbit just above the surface of the Earth, like this, so just grazing. By the way, things in low Earth orbit are usually a few hundred kilometers up, but that's relatively small height compared to the size of the Earth itself, which is 6,000 kilometers in radius, right? 6,400. So it's the radius of the Earth. So what we're going to calculate now, as far as linear speed and period, even though it's for something just grazing the surface of the Earth, scraping the mountaintops, it's actually very close to these numbers for anything that is in low Earth orbit, which is things like the space station, for example, or previously the space shuttle, right? Or now the new SpaceX spacecraft that's up there right now. Okay, so we know that for circular orbit, we know that the speed that an object should have, the linear speed or tangential speed that it should have in that orbit, is equal to big G, mass of the central body, right? So in that case, that's the Earth. It doesn't matter what the mass of this little satellite is, as long as it's much smaller than the mass of the central body. Then this equation holds. Divided by the size of the orbital radius. So what we're going to do is, in this case, this is going to be equal to big G, mass of the Earth, divided by radius of the Earth, right? So we're assuming that this orbital radius is just above the surface of the Earth. All right, great. So let's plug in those values. So that's my big G, and then I have the mass of the Earth. And then I have the radius of the Earth. And I take the square root of that whole thing. And I ask my calculator what that is, and I get roughly 7,900 meters per second. And if you convert that to miles per hour, that's about 18,000 miles an hour. Or as you can see, it's about 8 kilometers per second, or about 5 miles per second. So rounding to either 3 or 2 sig figs, that's about 7.9, let's say 2 sig figs, kilometers per second. Although it looks like, really, I know all these values to 3 sig figs, so I could have left it at. Let's do that. All right. Now, once we know the speed of something in circular orbit, how do we find the period? Okay, well, we know that for uniform circular motion from our previous lecture, I'll switch colors just for now. Speed is equal to circumference divided by period. So one way for us to answer this is just to say, okay, the period of something in this orbit must be 2 pi r divided by the speed. So that's 2 pi times the radius of the Earth divided by the speed. And when I calculate that, I get 5,073 seconds, right? All the answer choices here are given in hours. So it looks like if I convert that into hours, I know that there are 3,600 seconds in 1 hour. So that turns out to be about 1.41 hours. So it turns out that's very close. This is about 100 minutes. That's about exactly the orbital period of other things in low Earth orbit. So like I said, the space station or any other satellites that are in low Earth orbit, if you've ever seen a tiny little satellite dot in the sky zipping along, it's circling the Earth once every 100 minutes or so. Another way to solve this would be to use Kepler's third law. And for that, we would not need to have found the speed previously. We would just be able to use this information and calculate the orbital period directly. T squared is equal to 4 pi squared over g, mass of the central body, which in this case is the Earth, times the orbital radius cubed. So what that means is in this case, T would be equal to 4 pi squared over g, mass of the Earth, times radius of the Earth cubed. And then we got to make sure we take the square root of that whole thing. If we plug in all of those values, we would get the same answer, 5,073, or close to it, probably slightly off in that fourth decimal place, seconds. All right, great. So that concludes lecture 1718. So I recommend that you try as many more of these sample problems on the tutorials as you'd like, or just go directly to online homework 16-18 and try the remaining gravitation and orbit problems that are on the online homework.